In today's Tiny Methods workshop, we'll be taking a look at graphing in R. First, we'll consider how to create graphs using base R, so you don't need to install any additional packages. And then we'll be moving into consideration of the ggplot2 package, which allows us some additional graphing functionalities. So let's go ahead and jump right in. Okay, so as you can see, we'll be working with R via the RStudio interface here. And just a quick introduction if you're not familiar with R or RStudio, in the top left-hand window, we have the script editor, which allows us to write some commands. We'll run them from there as well. Below that, we have the console. This is sort of the brain of R, where our commands are actually being executed. To the top right-hand window, we have an environment tab and a history tab. The environment tab will show any objects that we create, any data sets that we read in. The history tab will show a running log of any commands that we've executed up to this point. And then in the lower right-hand window, we have 5 tabs here. We have a Files tab, which shows us the files that we have access to on our computer here. Then the Plots tab is where we'll be focusing mostly today. This is where our graphs will appear. We also have a Packages tab. This is where you can install and read into your library packages. Then the Help tab, you go here for help. If you're concerned or confused about any of the functions we'll be talking about, you can type them in right here and it will give you additional information on those functions. And then the viewer back here, we won't worry about that. All right, so let's switch back to the Plots tab since that's where we will be creating our graphs. Okay, so focusing back in this upper left-hand window, we can see that we're going to be working with a data set from the General Social Survey. We have 843 cases in this example, selected from the 2006 administration of the survey. If you want to read more about the survey, I included the link there that you can go check out. Then the first step is to read in your data. We need something to work with. So that is happening on line 14. And you need to make sure to update this path to wherever your data are located. So if you've downloaded these data, which are in the GSS 2006_TMW example.csv file, if you've downloaded that, this will need to specify where you've downloaded that to. And header equals true here. This just indicates that we have variable names in our data set. And then I wrote out the variable descriptions here for the 16 items in the data set. I'm going to switch back over to the environment tab here so you can see if you've read in the data correctly, you should have 843 observations, like we mentioned, across 16 variables. And those 16 variables include 5 physician trust items, which you can read the actual wording here if you'd like. They are rated on 1 from strongly agree to 5 strongly disagree. And then we also have a PT scale, which is capturing something about physician trust by taking the average across these 5 PT prefix items above. Then in terms of demographics, we have an age variable that's measured in years, a years of education variable, a race of respondent variable, which has 3 categories, white, black, and other. Then we have a married indicator. Is the person currently married? 0 is no, 1 is yes. A full-time indicator, is the person currently employed full-time? 0 if no, 1 if yes. Parental status, 0 if no children, 1 if they have children. A female indicator, which is 0 if they're male, 1 if female. Then we have home pop, which is the number of people in the household. Then we have the SCID class. This is subjective class identification. So the respondents were asked to identify their class. And we have 5 categories here, 1 lower class, 2 working class, 3 middle class, 4 upper middle class, and 5 upper class. And then we have region, which is the region of residence, and these are the 9 census regions as well. And then below that, we have some data prep. What we're doing here is treating each of the categorical variables that we just discussed above. So most of the demographics, except for age, education in years, and home population. So the other ones are all categorical, and we need to make sure to treat them as such. We can do that in R using the factor function where we specify which variable we're working with. In this case, the first one here is race on line 50. The levels are 1, 2, and 3. We saw that above. We have 1, 2, and 3. And then the corresponding categories are white, black, and other. And I'm assigning that to a new variable in the same data set called race F. Just F is here indicating that it's a factor. And the same applies to all of the other categorical variables we have as well. Right, and then we will start by looking at some of the basic graphing functionalities in R. So I mentioned before that you don't need to install any additional packages here. There is one exception to that at the end, but we'll start with ones where you don't need to install any additional packages. So if you have R on your computer, you're working with it, you can go ahead and run these lines without doing anything else. So first, let's build some histograms for continuous variables. The function for that is hist, H-I-S-T. The first argument is the variable you're working with. In this case, we're working with the age variable out of the data set. So data $age gives us the age variable. Then I'm changing the main title here to be age in years, so just something descriptive. And then the X label, so this is on the X axis, will be age. So we go ahead and run line 77 here, which you can run the lines in this script many different ways. You can either have your cursor in the line, hit this run button up in the upper right hand portion of this upper left hand window, or you can use a shortcut on your keyboard, Control Enter will also run that line. Okay, so we can see our histogram over in the plots window now. We see our main title is age in years, our x-axis label is age, and we do have a histogram, so that's good. If we want to look at another variable, for example, we can look at the education in years variable. So the setup is the same, hist for the function building the histogram, then data $edu_years to get the education in years variable out of the data set, changing the main title to years of education, changing the x-axis label to years, and then here we're going to be changing the limits of the x-axis as well as the limits of the y-axis. So we'll take a look at this first, running line 78, so we can see what this looks like. And just so we can see what these arguments do, let's go ahead and take out these changes to the x and y axes. Right, and let's actually take out this x label as well, so we can see what that looks like without specifying what we want it to be. So I'm going to rerun line 78 there, and we can see the changes. So we can toggle between these using the little blue arrows at the top of the plots window. So this is the last one, the one we just created. We didn't specify anything about the x-axis, about the y-axis, or change the label on the x-axis here. We can see that if we don't do that, we get data $edu_years, which is pretty ugly. It's better if we would change that to something like education like we had before. And then if we look at the x-axis here, we can see that we have some cases hanging out over to the left of 5. That looks not quite nice. And if we look at the y-axis, we can also see that our tallest bar here is above highest label, which is also not very good looking. So if we modify those things by changing the x-axis and the y-axis, as well as cleaning up this label for the x-axis, we get the plot we saw before this, which looks like this. So now our x-axis fully covers our observations. Our tallest bar here is not above the y-axis. And then this says years. I said education before, but it says years here, so that makes sense. These are the years along the x-axis. So this plot definitely looks cleaner than this one. And again, over here, I will undo the changes I made just so we can see what that looked like. So this is the one creating this cleaner plot. And these are just a few of the specifications that you can make for each of your graphs. We won't be covering all of them today because there are a lot and they do differ by function, but these are a few. If you're interested in learning more about what you can change about these plots, like I mentioned, go over to the Help tab, type in hist in this case, and then you can read about all of the arguments that go into this function. Okay, returning then to our histogram examples here. So this next bit here, well, let's just run it and then we'll talk about what it does. Okay, so you can see now that we have the counts in each of these bins of our histogram included on our plot. And what we're doing here is adding text, and we're adding it at the midpoints for each bin. And what we're adding are the counts. So this hist_ed, I saved the original histogram that we created under a name, and this is pulling out pieces of this object here, including the midpoints and the counts for each bin. And then the labels are also the counts. That's what we want plotted on our graph. And then these adjustments are just moving the labels around so that they show up nicely on the tops of the bars. And one more example for histograms, if we want to look at the physician trust scale, we can do that with data $PT scale, again changing the main title, changing the x-axis label, and we can see a plot that looks like this. So then moving into some density plots, also for continuous variables. This is another way to look at the three variables that we've seen already. So starting with age, again here, we're going to do is plot the density for this age variable, which is in the data set. And then we're also going to give it a main title. So running line 84 here, we get a density plot that looks like this. And then for a couple of more examples of density plots, we can do the same thing for the years of education. So in line 85 here, the only things that are changing is the variable specified, so data $edu_years, and then changing the main title in accordance. We can have the density plot for that. That one looks nice and interesting. And then we can also look at the density plot for the physician trust scale on 86 here, again changing the variable name, so it's data $PT scale, and then main equals physician trust, so changing the main title to physician trust. Then continuing with the continuous variable plots, we can look at box plots. And the function for box plots is box plot. The first argument, again, is data $age, and then changing the main title once more here. And we get a box plot for our age in years variable. Similarly, for the education years here, 90, we get a box plot there. Notice that we do have 4 low-lying outliers in this case. We can see the little dots hanging out below the main body of the box plot. And then we also have one more here for the physician trust scale, and we also have some low-lying outliers for this one. And that concludes then the first section on some univariate graphs for continuous variables. If you do have any questions on interpretation of these graphs, it's not the focus for this particular workshop, but do feel free to reach out, which I will talk at the end about how you can reach out, but feel free to reach out to us with any questions about interpretation of these graphs or any further details that you would like on the process of graphing as well. So moving then into a few graphs for categorical variables, we're going to build a bar plot here. So there's a little bit of prep we need to do first. We're going to create a table of counts for our race variable, which had 3 levels, white, black, and other. So the function to create this little table that we need is table, and then the argument for that is data $race f. Notice that f is the factor version of the race variable that we talked about at the beginning. And if we run line 94 here, and I am saving this table in counts_race, just so we have this table stored elsewhere because we will be using those counts in the bar plot. We can see we have 658 respondents who identified as white, 140 who identified as black, and 45 who identified as other. And then to build the bar plot here, the function is bar plot. Then the first argument is counts_race, so this is just this table of counts. It contains the counts for our 3 categories. Then main does what it did above, is changing the main title for the graph. Ylab does what it did above, well, in the x-axis case, but this changes the label of the y-axis. And then ylim, again, does what it did above, it changes the limits on the y-axis. And then I'm saving all of this to bar_race. So if we create this bar plot here, we can see it in our plots tab. So we do have 3 bars for our 3 levels in this variable. And something interesting about this plot is the bars seem to be floating sort of out in space. There is no line across the origin. So if you do want to add that horizontal line at the origin, you can do it with a b line, h equals 0. So we're adding a straight line at height equals 0. So I ran line 97, and now we have a origin for our bars. And then on the next line here, we have text. So we saw this above as well. It allows you to add text to your plot. I was playing around with this so you see it down in the console now and up on the counts because, well, you can see that first number does not look nice. But let's walk through the specification of this particular line on 98. So text, then x equals this bar_race is where we've saved our bar plot. Then y equals counts_race. This is the frequency, so we're moving up and down the y-axis according to the corresponding frequencies for each bar. Then counts underscore race, recall this is where we've stored our table of counts, and these are what we're actually going to be plotting on our graph. Position equals 3, you can see that in the little plot already over to your right now, that this adds it above the bars, and you can change that to 1, 2, and 4 and experiment and see where it sticks the text. And then CX here, this is changing the size of the text that you're adding. So if it's 1, that's the standard. If you decrease it to 0.8, it makes it smaller. If you make it larger than 1, 1.2, whatever, will make the text larger. You can see with the current sizing of this plot window over here, we can't actually see the full top of the 658 that's supposed to be above the white bar. So if we change this, maybe we can actually see the full number. Let's recreate this plot without the counts on it first, add the horizontal line back on, and then play with this argument back here. So say let's make it 0.5. And then we can see the counts. They're pretty small in this case. Maybe not the best thing to read, so we can also increase that if we like. Again, we'll start over creating a fresh bar chart, adding the horizontal line, and then let's try this at maybe 0.65. So there we're still getting that cutoff. So this is something that you can play with to get the graph looking nice. If you make this window bigger, the plots window, resize it, that can also influence how your graph looks, and I'll just show an example of that. If you stretch it out like this, you can see it gets wider than it was before. We can increase the height here as well. And now we can see the full 658. So what I had with 0.8 earlier, that worked fine when I had this screen full size. It's not currently full size. So when I made the screen smaller, the 0.8 was too big to actually see all of the numbers. All right, so let's go ahead and reduce this back down just so we can see everything else. But we don't need to see all this stuff up in the environment tab. Okay. So let's take a look at another example. Let's do one for region here. So this is the region of residence. There were 9 options corresponding to the 9 census regions. And on line 100, we're creating, again, a table of counts. So table data $ region F, again, to get the version that's properly treated as a categorical variable. And then we're going to save that as counts underscore region. And we can see our counts for our 9 regions here. Then if we want to build a bar plot following the same process that we just saw, bar plot, counts underscore region is the table we just created. Main, we're going to title that region of residence, label the y-axis frequency, change the limits on the y-axis as well. And then we'll see here that this call equals white is actually going to change the color. That's what it's short for, the specifications of our graph. So let's go ahead and take a look at that. And I did save this bar plot as bar underscore region because, again, we're going to work with it later when we're working with, for example, the text function. So if we look over at our plot now, we can see that the bars are no longer gray like they were in our respondent race plot. Instead, they are white like we specified. If you wanted a different color here, feel free to play with this parameter and change the appearance of your graph. All right, so this is a little bit of a messy graph. We do have a lot of categories happening. And even if we space it out, we still can't see all 9. So we don't know exactly what's being labeled here. We can only see 5 names even in this wider version, which isn't ideal. So we can change up how the labels for each bar are created. And this is a bit of a long process, but we'll walk through it. So first, let's go ahead and create a bar plot. In this case, I put no X name, so we don't want any labels on our x-axis at all. So the only thing that really changes here is this. Axis names equals false. So I did include a comment saying that this does indicate that we want no x-axis labels. Everything else is staying the same. So if we run line 103, you notice we don't get any labels now on our x-axis. So what we're going to do after we add in our horizontal line to again ground our bars so they're not just floating about, we're going to customize our x-axis labels. And the first step here is to add some ticks for each bar. We'll see what this looks like. So to do so, axis is the function you're working with. Side equals 1. This is indicating we want the bottom. Labels equals false. We don't want anything labeled here. We just want our tick marks. And we want these at the locations in this object. So let's take a look at what bar region no X name actually gives us. And if we take a look here, what it's giving us is actually these locations along our x-axis. And we want the tick marks at the midpoints for each bar, is what's happening here. Okay, so let's do that and see what that looks like. So now we can see these little tick marks added at the midpoint for each bar. And the next step then is to add the rotated labels. And you can see that they're already over on the right because I did notice an error in the current code I'm working with, which I will fix before I upload the script. But instead of being bar underscore region here, we should be working with the no X name graph that we created above. So no X name in both of these places. And again, I will fix this in the code that's uploaded, but I have to do it live right now. So let's go back to this original bar graph with nothing added, adding in the horizontal line, adding in those tick marks that we talked about. Okay, so now we're back to where we were. Okay, so then the next step is going to be add in those rotated labels that we want. So we're going to do that with the text function. Again, X is specifying this bar plot that we created, bar region no X name. We saw before that this is giving us the midpoints along the x-axis where the bars are located. Then this y par USR, this par USR part is giving us the parameters that are the furthest x location to the left, the furthest x location to the right, so the limits of the x-axis. Then the same thing for y, the lowest y and the highest y. And what we want out of that is the third of those. We want the lowest y that's in our graphing region here. So that par, USR, and then 3, we're indexing the third element out of this par vector that we have. And this will give us the lowest place for our y-axis. Let's actually just take a look at that so we can see. So we can see that's 0, which makes sense. We see that our lowest point on our y-axis is 0. And then we want to plot these labels, but we don't want to plot them right on 0. That would not be pretty looking. So we need to drop them down a little bit lower in our graph. And we're going to do that by subtracting 12. 12 was a number that I ended up at after I played around with this a little bit. So you can just play again with this number until the graph looks right to you. And what we're actually adding at this location that we're specifying with all of these other pieces are the names of this counts region. So these are the regions. And those are the labels that we're going to be putting on our graph. And this XPD equals NA here, this allows us to write below the graphing area. Otherwise, it would cut off the bottom part of our labels, which we don't want. We want to be able to write below the graph. So that's what that is allowing us to do. Then this SRT is rotating our text. And with 40 here, we're rotating to 40 degrees. Again, this is something you can play around with to find something that looks nice. Add here is adjusting. This is text justification, really. 0 is left justified, 0.5 is centered, and 1 is right justified. So this is shifting our labels to the left so that the right-hand part is justified underneath the axis tick points that we've made. And we've seen this CEX before. This is changing the size of the text. Let's go ahead and look at that. So running line 108 then gave us these tilted labels so that we can actually see each of our regions appropriately corresponding to their bar in the plot. Then the last thing we're going to do is something we've already seen. We're going to add the counts for each bar so we can see how many people fell in each of these categories. We're going to be doing that with the text function once more. Again, we're adding on to this bar region no X name. This X here is giving the midpoints along the X-axis. Y is the frequency or the count, so we're moving up the Y-axis. Then what we're putting there is the actual counts for each of our regions. Pause position equals 1. So this is different than what we've seen before. Position equals 3 is above. Position equals 1 is below here. And then we've also seen CEX, which is changing the size of the text. So adding the counts on here is what we did in line 110. Okay, and then moving on to one more type of plot before we move on to the ggplot2 function is scatterplots. So this allows us to look at two variables at a time. So we're going to be looking at two of our continuous variables here. So we're going to start with the plot function. This allows us to build a scatter plot when we specify two actual variables. So the first one is going to be data $age. The other one is data $PT scale. So we're creating a scatter plot for the age and physician trust scale variables. The label on the x-axis we're specifying is age in years. The y label is physician trust, and we're also giving it a main title. And we can see what that scatter plot looks like here, which is kind of a messy scatter plot. We're not gathering too much from that, but we do have a scatter plot. And if you want to add in the simple linear regression line, you can do that as well. The function for that is AB line here, so we're adding in a straight line. And the line we're adding in is according to LM here, linear model, where our y is the physician trust scale, the x is data $age, and then color, I just specified blue here. Feel free to play around with the colors if you'd like. So all we've added there is the linear regression model, which you can see is very, very, very slightly sloped upwards, but the relationship between these two variables isn't particularly strong. Then for another example of a scatter plot, we can do a similar thing for the age variable, but change the second variable here to the education in years variable that we have. And make sure to update the y-axis, which I just called education here, and to change the main title. So we have another scatter plot, which is also a bit all over the place, but we can take a look at it. If we want to add the linear regression line, again, AB line, LM, the y here is the education in years, x is age, and then we have a different color. We'll play with deep pink. So then we have a regression line there, which is also sloping slightly negatively, but not too strongly. Okay, and then I did mention earlier that there is one place here where we're going to be requiring another package that doesn't come with just base R, and this is the car package, which to install this package is install.packages, specify car. I've already installed it, so I'm not going to run line 123 here, but I am going to read it into my library on 124. So install the package on 123. You only have to do that once on your computer, but you do need to read it into your library every time you're working in R. So I'm going to run line 124 to read in the car package. And now we have some additional functionality. And the reason we're using this package is to build some scatterplot, well, to build a scatterplot matrix. And if we look at the names in our data set, so this is telling us what our variables are. Essentially, we know we have 16 of them, and this is what they're called. We've seen their actual descriptions above. But what we need this for is to select the continuous variable so we can build these scatterplots. The function is scatterplot matrix. Notice that this M in matrix is capitalized. Then the first argument here is data. We want variables 6 through 8. So that little colon in between is telling us 6, 7, 8, 6 to 8. And if we look down in the console, we can see that 6 is PT scale, 7 is age, and 8 is education in years, which are the continuous variables that we want. So we want to plot those three variables in a scatterplot matrix. Color is black here. Again, you can change that to whatever you like. And then smooth equals F or false. Just type that out so you can see what that is. This is turning off the non-parametric smoother that this function does allow for. So let's run line 127 there. And then like we were wanting, we have a scatterplot matrix. So we can see all three of the bivariate scatter plots for our three continuous variables. And you do notice also that like thick black line, that is the linear regression line that we created separately in the plots above. And the nice thing about this scatterplot matrix, you do also get the density plots for each of your variables running down the diagonal. Okay, so that is the first section in this workshop, working with base R to create plots. And we're going to create the same plots using the ggplot2 package. So again, you'll need to install this package if you haven't done so, and then read it into your library. then we'll start back with building a histogram. So the way that we write this out here is first indicating, well, we're going to plot. So ggplot, we're building a plot. And then we need to specify that the data set, in this case, is just called data. And then we want to be working with this variable age, x equals age. So AES, x equals age. If you wanted to change that to education, we would use the educ_years. Then what kind of graph we want to build, in this case, is a histogram. So then we add, so there's a little plus sign there, geom_histogram. So this allows us to build a basic histogram. And then there's open parentheses at the end here. We don't include anything yet. We will, in a moment, add in some additional specifications, but for now we just want basic histogram. So running line 137, we do get a basic histogram. So we can see that this is for our age variable on the x-axis. The y, this does show the counts, and we can see our bars. If we want to add some specifications to this to make it look a little bit nicer, we can do that. So the first part stays the same, ggplot, data, AES, in parentheses, x equals age for the variable we're working with, and then geom_histogram to build a histogram, and then we add in our specifications. So color equals black here, fill equals gray. Color is going to give us the outline of each of these little bars. Fill is going to be the color inside, so gray. Then we're also going to add some labels. So notice a little plus sign. Moving down into line 141, the labels that we're adding here are the title, which we're going to call age in years. We're going to adjust this x-axis because it is lowercase and it looks nicer with a capital letter, so we'll just make it age with a capital A. And then we'll also change the y-axis from count to frequency. Then we're also going to add, so a little plus sign again, a particular element here to our graph is centering the main title. So we do that with this theme here, and plot.title, so the title of the plot. We do want to change an element of the text, so element_text. What we're doing is changing the horizontal justification, and 0.5 is for center. So we'll run line, well, 139, 140, 141, and 142 all together. If you just put your cursor in line 139 and run that, well, if we can run it right, there we go. It will run all of those for you. So now we can see this updated histogram that we have. We do have our bars outlined in black. The fill is gray. We can see labels on the X and Y axis that we created, as well as a main title. And the main title is centered. Just as an example of what would happen if you didn't include this last line here, notice that the title is left justified. But if you do want it centered, you need to add that plus theme plot.title, element_text, and then horizontal justification 0.5 for center. And I did again include comments over here indicating what each piece does. All right, and then you may have noticed we get this little red text in the actual console indicating that we're currently using 30 bins, but it says you can pick a better value with bin width. So maybe we think 30 bins is too much, too many. So we want to reduce the number of bins, we can do that. We follow the same process. The only thing that we're changing between 139 and 142 into 144 and 147 here is this bins equals 15. We are changing the number of bins. We're making fewer bins. And if we run lines 144 and 147 then, we do get fewer bins. So we can see that. Let's toggle between the two just so we can see the difference. So we have quite a few bins in this one. If we reduce the number, we have this one. Okay, and then the next thing that we're going to do is take a look at histograms by group. So this is not something we did above. This is a pretty nice feature of ggplot that allows us to look at, again, histograms by group. So say that we think we're really interested in the age distribution by whether someone is considered a full-time worker or not. So what we're going to do here is following a similar process. So oops, let's move that. ggplot, data, again, specifying your data set, AES x equals age. So we're building histograms for the age variable. Then what we want to do is specify the color and the fill of the graph, so color and fill, by this second grouping variable, which is full-time F, which was a binary indicator of whether someone was full-time employed or not. And then this next section is the same that we saw above. First, we have geom_histogram to build a histogram. Bins equals 15, so we are using a smaller number of bins here. Position equals identity. I'll scroll over so you can see what that says. So identity gives overlaid histograms, and we'll see what that looks like. There are other ways to do this. You can sort of like stagger your histograms. So what we're going to do is really just plot these on top of each other, and we're going to adjust the transparency of the colors themselves so that we can actually see that one is on top of the other. We don't block one with the one in front of it. There we go. So alpha equals 0.5. This is creating more transparency. It's making the one in front, well, and the one in back lighter so we can see both of the histograms that are going to be plotted. Then the labels here are similar. We've seen the title before, X and Y. Then what we're doing also is changing the color and fill here. And what this is going to do is clean up the legend that we'll see in a moment. Because anytime you are plotting by groups, you will get a legend so we know which color goes with which group. And then theme, similar, centering the plot title first. And then this next part, legend dot position equals bottom. This is specifying the legend position. You can do bottom, right, left, top. Feel free to move that around. Okay, so let's go ahead and run that so we can see what it looks like. So we do have then our histograms by group. We can see by looking at the legend that is on the bottom, like we specified, that those that are not employed full-time are in this sort of salmon colored, and those that are in this teal color. And we can see these overlaid histograms above. And what might sort of be expected is, if we look at the ones that are full-time employed, that tends to be pushed a little bit to the lower ages, whereas not being full-time employed is pretty fairly evenly distributed from the lowest age to the highest age, with a tapering off as we get into the highest observed ages. Something I didn't mention here, if we're looking at the line 154, where it has employed, and then you see a slash in full-time, a backslash in full-time, this backslash in is, well, let's just take it out so we can see the difference. And if you're unsure about what something does in this code, feel free to take it out and see what happens. You may just get a warning that it can't run, but it may just change something and you can understand a little bit closer what each element is doing. So if we don't add in that slash in, notice that everything just runs together. So we can see that in this bottom right hand thing. Everything just is all smashed together. If we insert this backslash in, it gives us a new line. So we have employed, and then it's no longer smushed. This full-time is below it. Then moving on to our next type of graph here, density plots. So the first setup is the same. ggplot, we're working with the data set, and we're working with the age variable there. Then what's new here is geom_density to give us the density, that's what we want to plot. And then xlim 0 to 100, we're changing the limits on the x-axis, which we've also seen above. And this gives us a basic density plot. We can look at that. It looks like the density plots that we saw when we were working with base R. If we want to customize this density plot, we can do that as well. So we'll be adding in some specifications into this geom density portion. We can change the color, which is the outline part. We'll just leave that as black actually. Change the fill to light green. It is spring, so let's incorporate some spring colors. Then we've seen this changing of the limits of the x-axis before. We've also seen labels above, adding a main title, adding in a, well, adjusting the label on the x-axis, adjusting the label on the y-axis. I'm really just capitalizing them because I think it looks nicer. And then we are centering the main title using this theme, plot.title, equals element_text, again, horizontal justified, 0.5 gives us centered. So running line 160, we now have our customized graph. Just like we did with the histograms, we can also create the density plots by group, and this follows similar setup. So ggplot, working with the data set, our variable that we're creating the density plots for is age, x equals age. Then we're going to be specifying color by the levels in race, F, and fill by the levels in race F. Then the geom underscore density, we are adding in this alpha equals 0.5 because we do have two overlaid plots in this case. And if we want to be able to see both, we need to increase the transparency so that we can see both of them on there. Then the labels, color, and fill here, so we know that that corresponds to race, which will show up in our legend. And then adding into this theme component, legend.position equals right. So we've seen above where we had put it at the bottom. In this case, we can put it at the right. So line 167 here gives us this plot. Recall that the race variable did have 3 categories. So we do have 3 overlay density plots here. And we can see that the salmon color again is for the white category, the green color is for the black category, and the blue color is for the other. And you can change those colors if you're interested in kind of customizing this even further. Otherwise, you just get the default differentiation with these 3 colors. But if you want to change that, you can do that as well. Just for an example here, let's change this alpha to 0.25. So let's half it here. See how those became more transparent? And conversely, if we make this up to like 0.75, it will become more opaque. I'm just going to set that back to 0.5 since that's where we started. Then moving on to box plots. So there are 2 ways to do this here, depending on whether you put in the AES portion y equals age or x equals age. If you put y equals age, you get a vertical box plot. If you put x equals age, you get a horizontal box plot. And let's just look at both of those. So 175, ggplot, working with the data set. Y equals age, so we will get a vertical box plot here. And then we need to specify geom underscore box plot to actually plot a box plot. And we can see that we have a typical vertical box plot. This is a lot like what earlier. And if we would like to create a horizontal box plot, which tips this box plot on its side, we can do that by specifying x equals age instead of y equals age. And then we get a box plot running horizontally. And then, like we've been doing before, we can add some customizations to these graphs. So we'll just tilt this back up to a vertical box plot since that's what we also saw with base R. And then we can change the label. So y equals age in years here. And then we can also play around with the, let's actually tilt this back up since we're going to be working with vertical ones. If we look at theme, axis.text.x equals element blank, this removes the x-axis label. So down there we can see -0.4, -0.2, 0, 0.2, 0.4. Those aren't really meaningful, so we can just get rid of those labels. We don't need them here. And similarly, we can also get rid of the ticks, so the little tick marks down there. So axis.ticks.x equals element blank. This element blank removes those 2 elements of the graph. So running line 178, we can see now that our x-axis is clean. We don't have those labels hanging out down there anymore. And our y-axis label now is age in years. And let's look at another example. So the education in years variable, if you recall, it did have outliers. It had some low-lying outliers that the age in years variable did not. So if we want to play around with how the outliers are shown, we can also do that. So we're changing the variable to y equals edu underscore years here. And then in the geom box plot portion, we're specifying the outlier.color equals red. Again, you can play with the color. And outlier.shape equals 7. So there are a lot of different shapes. Feel free to play around with the numbers here and see what shapes they give you. And then the label is staying the same, and we're also getting rid of the text and the ticks on the x-axis. So running line 183, we can see now that we have little red marks for our outliers. And actually, let's just change the shape and see what other options we have. So now we have stars. If we move up to 9, we have sort of diamonds with crosses in them. So feel free to play with that number to change the shape of the marker for your outliers. And if you don't do that, they're just plain black circles. Okay, and then looking at bar plots for our categorical variables. This is a similar setup. ggplot, data is the data set we're working with, AES, X equals married F. So let's look at the indicator whether the person was currently married or not. And then geom underscore bar, we're building a bar plot. And what we want on our y-axis here is the count. So this is building a basic bar plot. So we can see we do have the count on the y-axis. We have our two categories. No, they're not currently married, or yes, they are. Just like we've been doing, we can add in some additional specifications. And that begins on, well, it begins right here, actually, on line 192, because we are going to be specifying a bar-specific color. So we want our two bars to be different colors. We want them to be different colors according to their differences. So fill equals married F. So category 0 is going to have a different color than category 1. And then we're also changing the labels. We're adding a title, currently married, and changing the y-axis from count to frequency. Then we're going to be centering this title. So we've seen this, plot.title equals element underscore text. H_just horizontal justification, 0.5 views you centered. We don't want a legend here, so we'll take that out. We don't need one. We only have two categories. A legend is a little bit overkill for this graph. Then we are also removing the x-axis label. So this no and yes is going to stay there, but the married F part is going to go away because we are already indicating that this variable is indicating whether they're currently married or not. And then we have our bar for no and our bar for yes. And then finally down here, we're specifying the actual colors that we want our two bars to be. In this case, I didn't go with the sort of default that we would get. I did specify specific colors that I wanted to include. And so we can see this is scale underscore fill underscore manual. And this is allowing you to specify the actual colors that you want. And then the values here, see, this first one will give us the color for the no bar. The second one will give us the color for the yes bar. And these are hex codes, which you can find the actual values for online if you're interested in a particular color. Okay, so I ran line 192 all the way down to 198 here. And we do have a darkish red maroon bar for no and a green bar for yes. And then finishing up with scatter plots. The setup is similar. We have ggplot, the data set. The X here is age. We do also need to specify a Y because we do have two variables that we're plotting in a scatter plot. And we'll use the physician trust scale here. And then the actual graph that we want to create is a scatter plot. And what we need to indicate for that is geom underscore point. And just to create a basic one, we'll just leave the open parentheses there. And we get a basic scatter plot. If we want to add in some additional specifications, we can do that. So in the geom underscore point here, if we put shape equals 1, we do change the point shape. So right now we have closed circles. If you want open circles, shape equals 1. Adding in the labels, changing the labels so that they look a little bit nicer than what they currently are. So X, age in years, and Y, physician trust. And then we can also add a linear regression line like we did above if we want to do that. And we do that with geom underscore smooth, method equals LM. And just a note on that, be aware of where all these plus signs are because they are important. We're adding each of these components. Okay, so now we have our scatter plot for these two variables with that blue line that is the linear regression line. And we have a gray band around it. Those are the confidence bands. And this is like we saw before. There is a slight positive upward slope happening, but there doesn't seem to be a particularly strong linear relationship between these two variables. And then if we do want to look at the scatter plot by group, we can also do that. So what we're going to start off with is calling this thing scatter underscore parent because what we're going to be doing is creating a scatter plot for age and physician trust by the parental status, so whether someone is a parent or not. And the setup is similar, ggplot, data, AES, X equals age, Y equals PT scale. We saw that on 203 as well. But down here on 209 now we're adding color equals parent F. So what we're going to do is be changing the points on our scatter plot according to whether the person is a parent or not. Geom underscore point to give us the scatter plot. Then changing the labels to age and years, physician trust on the X and Y. And then specifying that the color is parental status indicating whether someone is a parent or not. So we'll go ahead and run that, 209. And unlike in the examples we've seen above, we don't get an immediate plot here. That's because I did save it into this thing called scatter_parent. To actually see it, we can type out scatter_parent, and then we do get the plot that we created. And we can note that the plot is the same as the one we saw above or previously. But now the points in our graph correspond to whether someone is a parent with the teal color or is not with the salmon color. And then if we want to add a linear regression line on top of that, we can do that just like we did on 206. We're doing this now on 213. We're taking this basic scatter plot that we have already, and we're adding this geom_smooth method equals LM to give us a linear regression line. And then we do get our regression lines on our graph. And I did this in multiple steps from 209 to 213, but if you know from the start that you want to add those linear regression lines, you can do it all in one step like we did in 203 to 206. And then let's just take a look at the scatter plot that we've created. So if we focus in on the salmon colored points for those without children, we can see a little bit of a negative slope there to where with increased age, physician trust tends to decrease. And that is in comparison to the ones with children, where we see with an increase in age, we see a little bit of an increase in physician trust as well. But notice those are not very strong slopes whatsoever. And if we actually look at the correlation between the two, the Pearson's correlation, we can see for age and PT scale for the parents. So this is the teal colored information in the graph. It's only 0.072. And for the non-parents, it's negative 0.048. And then I did include the syntax below to get those Pearson's correlations if you're interested in doing that by just splitting the data set into a sub-data set for parents, where we do that with parents equals data, and then we're pulling out the cases in which the data $parent variable equals 1. Notice a double equal sign there. This is a true-false condition. And if it is 1, so these people are parents, they're getting pulled into this parents data set. And on 220, in comparison, if this parent equals 0, so they do not have children in this case, they're pulled into a sub non-parents data set. And then the core function on 219 and 221 calculates the Pearson correlation between age and PT scale, either in the parents subdata set or the non-parents subdata set. So those just give you these correlation values that I indicated on 215 and 216 if you're interested in finding those for yourself. And that concludes this workshop on graphing in R. If you have any questions about anything that I talked about today, or you want to dig in a little bit deeper on the interpretations of some of these graphs, or how you specify certain characteristics that you like your graphs to have, feel free to reach out to us. We do have virtual consultations available. If you're interested in doing so, you can visit our website at education.indiana.edu/research-help, or email us as well at drhelp@indiana.edu.